Hey everyone, it's Mr. Canfield. I am actually starting over because I did a really bad job the first time through, so let's start over. So we're doing linear approximations part 2. We're going to finish this notes pack and do a bunch of real life examples. So let's start this out. It says, a ham is taken out of an oven which is set to a temperature of 425 degrees. When the ham comes out of the oven, it is set in a room which has a temperature of 68 degrees. So if you think about that, you're taking something out of a hot thing, putting it in a colder room, it's going to cool down. A meat thermometer is used to measure the temperature of the ham at this time, and a value of 156 degrees is recorded. 5 minutes later, the temperature of the ham is 132 degrees, and after 15 minutes, the temperature of the ham is 96 degrees. Use a linear approximation to determine the temperature of the ham after 20 minutes and after 2 hours. Is your estimate an overestimate or an underestimate, and why? Okay, so what I like to do is I like to take this and distill it into just a bunch of symbols. So I know that as soon as we take it out of the oven, it's 156 degrees. Did I read that right? Yeah. And then 5 minutes later, it's already down to 132 degrees. And then 15 minutes later, it's 96 degrees. So if we think about this on a graph, so here's 0 minutes, here's 5 minutes, and then here's 10, here's 15, here's 20. So if we think about this, it starts out at 0, it's at this 156. So here's 150, here's 100, here's 75. So at 0 minutes, it's like, you know, a little bit above. Then at 5 minutes, it's down here. And then at 15 minutes, it's down here. All right. So I know it's going to be going down, but I don't quite know how much. And so I can draw or I can estimate a tangent line by using the average rate of change, because I don't have f of x, so I can't find f prime. Like, ideally, I'd find f prime and then find f prime right here, and then use that to figure out what's going to be at 20. But since we don't have that, I'm going to estimate f prime at 15 by using my most relevant data, between 5 and 15, which is not great, but again, it's what we've got. So if I were to do f of 15 minus f of 5 over 15 minus 5, we'll get, so let's see, f of 15 is 96, f of 5 is 132, over 15 minus 5 is 10. 96 minus 132 is what, negative 36? Yeah, okay. So we get negative 3.6. So we divide that by 10, so we move the decimal place over 1. So our average rate of change here, so my m there is, you know, it's going to be about negative 3.6, so I can say y minus 96 is equal to negative 3.6 times x minus 15. And so, you know, now I can plug in 20 there and then add the 96 to both sides, and that'll be a good estimation of, wow, type in x, Canfield. We're going to say 20. 78. So according to this line, it's going to be down to 78. Now, I want to figure out if that's going to be an overestimate or an underestimate. And I also got to try 2 hours. Well, let's see, 2 hours. I don't plug 2 in here. I need to plug in 2 hours in terms of minutes. So that's 120 minutes. And so after 2 hours, I have that it would be negative 282 degrees. All right, so cool. All right, makes perfect sense. If you've never had a turkey be negative, or ham, sorry, a ham be negative 282 degrees, I need to insert some joke about, like, then you've never had my mom's cooking or something like that. But so clearly this linear approximation breaks down here. And if you think about it, there's really a floor. There's no way our temperature is ever going to get below 68 degrees. You don't put something out into a room and then it gets colder than the room. That's more of a chemistry thing, though, or is it physics? Like, I guess it depends on. Or what are you looking at? What is it in chemistry? The thing in chemistry, or heat transfer in physics. Like, who's got more Q and whatever. Okay. Ignore the off-topicness. So we now want to figure out, are these an overestimate or an underestimate? And so if I'm going to think about that, I don't have a solid enough graph to be able to figure out the concavity of it. Because if I knew the concavity, then I could tell you. But I do know that F prime is F double prime. And then the sign of that is going to help me with concavity. This is not entirely true, but it's close enough. So if only I could find the rate of change of the rate of change. Well, we know that this one's negative 3.6. What's this one? Well, let's see. 132 minus 156 divided by 5. So it decreased negative 4.8, then it decreased negative 3.6. Our rate of change is getting higher. I don't know if you can see that. So I'm decreasing by 4.8, then I'm only decreasing by 3.6. Because of that, this tells me that even though it's decreasing. Wait. Oh. I'm overthinking this. I didn't need to find that. Since F prime is decreasing, that tells me. Here, let me write this in words. F prime is decreasing. Canfield, hey, F prime's not decreasing. F prime went from this negative to a higher negative. F prime is increasing. That tells me that F double prime is positive, which tells me concave up. All right, let me try to restate that really quick. So F prime between these two was negative 3.6. F prime here was negative 4.8. That means that as we go along, we can kind of assume, or at least what we've been able to see so far is that F prime went from something negative to something less negative. F prime got greater. F prime is increasing. And so if F prime is increasing, that tells us that its derivative needs to be positive because F prime is slowly going up, even though it's currently a negative value. So since F prime is increasing, its derivative is positive, and that tells us that the original F is concave up. So since it's concave up, if we were to imagine this, it's not going to eventually curve back up. But remember that if it's concave up, that means that our estimates are underestimates. So 78 degrees is an underestimate, and negative 282, might be an underestimate. Just by a couple hundred degrees. Okay. Let's see what's next. The population of Switzerland since 1970 is given in the chart below. Populatio, N in millions. No, population in millions. Okay. So 6.3 million, 6.4 million, 6.7 million, 7.2 million, 7.8 million. Notice that these are going in tens. So every 10 years. Use a linear approximation to find the population of Switzerland in 1992, and in 2013, and in 2050. So we're going to need to use separate ones for these. Specifically, so 1992, that's between these 2 years, right? So we're actually going to want to use, which of these years is it closer to? Basically, we're either going to want to find like a tangent line at 1990 or at 2000. So 1990 and travel up to 92, or at 2000 and travel back to 92. But 1990 is closer to 1992. So, and this is where we would, if this was something I was doing for real, like for a company or something, where we're trying to get census data, or I guess that'd be the government, but like if I'm trying to get population data for a company for some reason, I'd want to try from 1980 to 1990, find that line, estimate it, and then do from 1990 to 2000, find that line and estimate it. Because these are going to be two slightly different lines. So like if we kind of look at that from 1980 to 1990, we have 6.7 minus 6.4 over 10. So that's 0.3 over 10. Right? Yeah, okay. So that's 0.03. And we could say y minus 6.7 is equal to 0.03 times x minus 1990. And that would be one of our tangent lines. And we could plug in 1992 in here and be able to handle it. But the other option is we can do 7.2 minus 6.7 over that 10-year span and also get a tangent line. This one, we get 0.5 over 10, which is 0.05. And so we have a slightly different slope. And so since we have a slightly different slope, so y minus 6.7 is equal to 0.03 x minus 1990. This is one of those situations where, depending on what data we use, we're going to get a different slope. It means we're going to get a different, Canfield, that's a 5. We're going to get a different slope, which means we're going to get a slightly different answer. We may even want to average those. For the sake of this class, like, don't overthink that. Excuse me. For the sake of this class, pick one, stick with it, just do it, like, whatever. Because, you know, we're more doing an exercise at this point than actually trying to solve a real-world problem. But if we look, those are the two slopes. Like, why don't I just average them? You know, or we could even, you know, what happens from 1980 to 2000, and try doing that. And there's lots of different data sets that we could use that would be, you know, good averages for us to try. So I think I'm going to stick with the 1990 to 2000 because that's the interval that this is actually on. So I think the 1990 to 2000 is going to be better out of these two, because that 0.05 is the average rate of change during these years. Instead of going, this was the average rate of change, let's extend it. This is the average rate of change here. Let's kind of carry that along. So then we would just take our 0.05 times our 1992 minus 1990 is 2. So I get 6.8. So 6.8 million people. 2013 and 2050, we would just need to go from 2000 to 2010. You wouldn't want to do 1970 to 2010 because, especially with population change, population tends to change exponentially. So the farther along we go, the greater the rate of change. And so if we were to take a whole span of years and find the average rate of change over those years, the average rate of change won't really make a whole lot of sense. Like, the population of the world has doubled in the last 100 years or something. Maybe it's a lot longer than that, but the population of the world doubles all the time. And so we don't want to go back and say, hey, 4,000 years ago, how many people were there? Oh, that means that every year we got this many thousand more people. It's like, no, population explodes at certain points. It's very interesting. You know, if you think about how many people there are and how much food we have, and don't get depressed. All right, so is your approximation of the Swiss population in 2013 an over or an underestimate? Well, since I know it's an exponential growth graph because it's population, that's a concave up graph, so that means that our estimate is going to be you know, an underestimate. Are you concerned about any of your answers? I am assuming that 2050 is going to be scary. All right, last example. So this, if you move on to Calc 2 next year, we're actually going to study a graph that kind of looks like this. This is called, it looks very similar to something called a logistic growth graph. And this kind of takes the idea of exponential growth, of population growth, and goes, okay, yeah, sure, things grow exponentially, but then there's like a ceiling to this. Like, yeah, the population of the world is growing exponentially, but what happens when we run out of space and when we run out of food? It's not going to keep growing then. It's going to start to peter off. So that's why it's swooping up, but then starting to slow down. All right. You can also do linear approximation of a graph instead of a chart or pure numerical data. Okay. This says, I cannot read that. Thousands. Wow. Okay. Thousands. Did I write that? Oh gosh. All right. No, it's in Comic Sans. I didn't write that. Okay. The graph given above shows the number of mosquitoes in a Florida nature reserve over the course of a 2-year period. So, and this is realistic, this idea that you're going to have a bunch of mosquitoes and they're going to grow and grow and grow and grow, but then we're going to kind of hit this ceiling where they can't breed fast enough to stay alive, or there's not enough resources, or the frogs are eating them, or the bug zappers are getting them. So, estimate the number of mosquitoes in the reserve after 7 months, 26 months, and after 50 months using a linear approximation. So, 7 months. I mean, 5,000? That's my guess. 26 months. All right, so here's 24 months. All right, so I'm gonna need to like estimate a slope here, aren't I? So, well, it looks like it goes up from about 20 to maybe 21 over those 3 years. So that's 1,000 every 3 years. And that's at 24. So I can say y minus 24 is equal to 1/3 times x. It's not the y value, you can't feel. 1/3, so x minus 24. My y value at 24, I'm going to say is 21. So y minus 21. So, okay. Hold on, the top of this paper is getting in the way for me. Okay. Cool. So, just trying to keep everything in frame. So if I were to plug 26 in here, that's only 2. So that's going to be 2/3 over here and then add it to 21. So 21 2/3. If you missed what I'm talking about, I'm just taking 1/3, plugging in 26, subtracting 24, then adding 21. That's all I'm doing. Okay. So, and K stands for thousands. I'm just abbreviating. So if we're going to try 50 months now, so 50 months. So the thing is, if you notice, my approximation is not going to be very good out at 50 months. Like if I were to try this, drop 50 months in, I don't think this is going to be a very good approximation, because over here it was rising 4,000 over these 3 years, and now we're down to just 1,000 in these 3 years. It's probably going to slow down even more. So it's not fair to say that every 3 years it goes up 1,000, but you know, using our linear approximation, I got 29 2/3 thousand is your estimate at 7 months, and under or over estimate, and the same about your estimate at 26. So it's 7 months. At 7 months, we have concave up. So at 7 months, at 7 months, my approximation is what it says on the curve. But if we were to do some kind of linear approximation, it'd be under. But 26, we have an inflection point in here where it's changing from concave up to concave down. So here, it's gonna be an over. Is your estimate at 50 months a good one? No. Defend your answer, why or why not? Because, oh, you didn't see me writing that. So this is, if this was a 3-point question, you'd get 1 point. So the reason it's not good at 50 months is because our rate of change is decreasing. So even at 26 months, we have an overestimate, and it's just going to be, judging by how this graph is going, we don't know what's going to happen that far out, but we can assume that it's not going to blow up like it did earlier on. But either way, our linear approximation is really only good for something really close by. So hope that helps. I will make sure that the assignment is in class, and yeah, we'll have a small quiz on this next time. See ya.